Okay, the 11th problem, or it's chapter 7, non-algorithmic question 23. So this one, I like this problem. It tells us draw the Lewis structure for the molecule CH3. So we're going to take CH3, CH2, CCH. So it's already given us a lot of information about that Lewis structure. And it's telling us that there's a methyl group, so that's going to be like that. Bonded to a what's called a methylene group, CH2. And then there's going to be a C without any hydrogens, and then another C with an H right there. Now, we still have to do the dot diagram. So let's count up the number of electrons. Carbon, carbon, 4 carbons, each with 4. So 16 valence electrons. And then there's going to be 6 hydrogens. So a total of 22 valence electrons. We put in 2, 4, 6, 8, 10, 12, 14, 16, 18. So minus 18 valence electrons. We still have 4 more to go. And they're going to go 2 pairs right there. Now we start looking at that carbon right there. It doesn't have any electrons. It needs a double bond. So does this one. So we can repair that by bringing one of these guys down there. Get rid of that. So that goes away. And then this one comes down, makes another double bond. That goes away. And what we see is that there's a triple bond between these. So the question is, how many sigma bonds? Well, 1, 2, 3, 4, 5, 6, 7, 8. There's one in between those carbons. 9 sigma bonds, and then 2 pi bonds. Now, what does that carbon look like that's right there? Well, there's a sp hybridization. That's sp. So that leaves 2 pi orbitals on either carbon, and they're perpendicular to one another, and that's what forms that double bond. That's the 2 double bonds. So that answer is 9 sigma bonds and 2 pi bonds. Okay, here we're working on nitrogen, fluorine, and neon. So they now have this order. So all of them, this is the normal order, that the S with a sigma from the P overlap is more stable than the pi. And we're just going to consider the number of electrons, put them in the molecular orbitals, and what we're trying to do is determine if there's any unpaired electrons, because that's the definition of paramagnetic. Is there any unpaired electrons that cause it to interact with a magnetic field? So we're looking at O2, 2 minus, we're looking at F2, 2 plus, we're looking at neon, 2, 2 plus, and we're looking at O2, 2 plus, and then none of the above. So we need to count up the number of electrons in this. So oxygen has 6. There's 2 of them, so that's going to be 12 electrons, but that's 2 minus. So we add 2 more electrons to make that 14 electrons in O2 minus. Now fluorine has 7 each, so 14 electrons, but it's 2 plus, so that means that's going to have 12 electrons in the molecule. Neon has 8. There's 2 of them, 16, but it's 2 plus. So that is 14 electrons as well. And then O2, 2 plus, well, O has 6 valence electrons. There's 2 of them. That's 12. It's 2 plus, so that's 10 valence electrons. Okay, and then we start putting them in. And I'm going to start with the lowest number first. So we've got 2, 4, 6, 8, 9, 10. I see no unpaired electrons, so that is not going to be paramagnetic. Now we go next to F2. We add 2 more electrons. 10 electrons is already on their diagram. We add 2 more, and those have to go in the 2 separate orbitals because Ohm's rule says they have to spread out. The electrons don't want to be near each other. And there's our paramagnetic, unpaired electrons right there at 12. And then the next 2 have 14, so we're going to add 2 more to that, and those 2 more are going to go right in there. So those don't have unpaired. Our only choice here is F2, 2 plus for unpaired electrons.